Welcome to everyone on the first video about the pass tutorial. In this video I will try to give you a general idea, so how I talked could be a good way to find a point for a pass. This, as I say, will just give you a general idea. Then in the next video I will show you how is the file structure, and then I'm going to tell you a little bit more in detail how the different stuff of the pass work. So first of all, let me start the pass simulation. So maybe I can just show you basically this. So let me just take away the legend. So first of all, we have three kind of pass. So the first one is the forward. This means that if here there is or door and here the opposite goalpost, we just throw the ball in this direction. This zone is lateral and forward, so we can either throw the ball like in this direction or like this. In this green area we just make either lateral pass or backward pass, and here in the red area we just shot to the opponent door. I hope you can see here what is the main so the setup for this simulation. So now let me take away all this drawing. So we have here our robot that we are considering, robot number 1, and here the other robot. First of all, what is done, so we have to discretize somehow the wall field. This is done by an instance of the class point field that I will present in another video, and this instance will create this field with all these points, and these are all the points that are going to be considered for a pass. When we have this point, we should consider what are the points around each robot where we could pass the ball. As you can see, I choose a square because first because we can access all these points like a matrix. So if we consider just the index, it's very easy to find out the index of the point around the point where the robot is. Secondly, because a lot of time we really want to use as pass point the point that is in the edge of our figure. So when we calculate, we have this point and we store all this point in a vector called possible index point or something like that with possible. After that, what we do, so we take the wall point field, so all this point, and we calculate the shadow that each robot can do. What does it mean, the shadow? So let's look at this example here. We have the robot here with the ball, and let's say that he would like to perform a pass to robot number 3. But as you can see, there is a robot in between, and the probability that the ball will hit this robot is quite high. So what we do, we calculate on the wall field the shadow, and the shadow is where the ball cannot be shot since it will hit something other. So of course for this calculation we use the ball. Why we use the ball and not the robot that could perform the pass? Because let's say that we have this situation, we should already perform the calculus using the final position where the robot is going to come. So when the robot detects the ball here, when he's coming to the ball, he should have already an idea where to throw the ball according to the position of the ball and not his ball. As you can see, the robot 2 make all this shadow, and this shadow will make so that all the point, so all the possible point around robot 3 will be seen as false. So every of these points has an index implicit because we point to this wall point field. but each of these points is composed of a coordinate xy, so a vector 2 in the Human code, and a boolean that tell us if it's true, like this point here that I'm indicated. This means true for a pass, valid for a pass, and all the white points that are considered as false. After that, we can select the right point and discard the point. So around each robot, as I showed you before, we have this possible index, so this possible point that could be used as a pass, but after that we calculate the shadows, we actually can get these red points, that these red points are the point where actually we could throw the ball. The yellow point will be therefore discard. And what we do, so what I did, I take, just in order to make faster the calculation, all these red points, and I store them in a vector. This vector is called point selected, or selected point. After that, we have to choose according to the zone, so according to the place where we are inside the field, the point where we want to throw the ball. Now I implement the stuff like that, so my is a first sketch of pass. For me, the most important stuff was to create the framework, so to create for you all this environment, for example, all these drawings, so the basic idea, in order to make more high-level logic for the pass, or also more complicated tactics. So let's start with the forward pass. The forward and the backward pass have the same idea. They are also, I also call them in the code sometimes front kick. Since is intended that the throw is the ball is thrown either if forward, so let's go in this direction, or backward in this direction from the front of the robot. So the robot will look at the ball and kick it. So as you can see here, we have two circles around the ball, so maybe I can take away all points. And these two cycles are the lowest distance that the pass should reach, and the biggest distance that the ball can reach. What do I mean with that? I mean that of course we have a maximum distance according to the carpet and to the implementation of the kick that the ball can reach, and a minimum that we want to set, because for example it doesn't make sense that a robot perform a pass of 20 centimeters. So the first condition is, that's always considering the ball as reference, the pass point should be between these two circles. Second condition, I talked, but this is just a first row of pass, that since so in the usual football player, normal ways we go on the lateral band in order to extend the play. So let's say that we have a lot of players here. Maybe we have one that is here, and this alone, so we want to throw the ball to him. So what we do, let's say that now we want to choose this player. We are going, if the ball is inside the orange band, it will find a point outside the orange band, and the opposite. If we are here, we are going to search a point here. And as you can see, in this case, if we're going to search, so always the point that with the x bigger as possible, and with the y also bigger as possible. According to that, the point, this green point that is here, I don't know if you are able to see that, but in this case is chosen as pass point. When we are able to find a point, then this will be communicated to the other robot, so that the other robot can move properly to the pass point. Then we have the other kind of pass, that is the lateral one. For the lateral one, we have this green box, so the point should be inside this green box. I will show you an example here. So let's move the ball like that. So for the lateral pass, I talked since we tested more the front kick rather than the lateral one. we want, so if we have to throw the ball away, so this means with always using the ball as reference with a big X, it's better to use a front kick rather than a lateral one. So I just make such that the lateral kick will go most in Y direction rather than in X. After that, so in this part of the field, we try to prefer, so we just perform forward pass. Here we prefer the forward pass, but if we are not able to find a forward point, we use the lateral kick. Here we prefer lateral kick, and if we don't find a point with the lateral kick, we are going to use the backward pass. All that in order to say that in this case, for example, we are not able to find a point with the forward pass, therefore we are going to consider the lateral pass to the to the other player. As you can see, we have the representation of this module that make all this calculation, that say the coordinate of the pass, that will say the distance. This is used by the in order to calculate the strength of the pass, the ID of the receiver, in this case is player number 3, and the type of pass, in this case it's lateral. Maybe last thing that I have to say, so maybe some of you may wondering why do we have some points that from the shadow are supposed to be not valid for the circle. So the shadow, sorry, I forgot to say that we always consider a circle around the robot, because is the space, the environment where the robot should come in the moment that the pass is done. So this is all stuff that are user defined. So we consider, of course, to the shadow all robot, but also the opponent. And in the opponent is set by default also the gold post. No, sorry. This means that in this case we don't have any opponent, but however the goal posts are always put as an opponent. Something that is really important, in order to see the opponent, we have to be the perception has to be activated. So in this case of this simulation, I suppose that the state of the robot, so his position is perfectly known. But in this way, we are not able to, so the robot are not able to see the opponent. So even if on the field we would have some opponent, they cannot be seen by the robot. As you can see, so if we don't find any pass point, what the robot should do is just to shot to the opponent goal. What I also implement at the moment is that this module, so as I explained in the previous tutorial, the module is run every time, so its function update is run every time. But here we have quite a lot of calculation, and since the pass will just be performed by the striker, so the robot that is closer to the ball, it doesn't make any sense that every robot perform all this calculation every time. So I set a distance, a minimum distance and a maximum distance, so that when the robot is approaching the ball, maybe I can make you a very small drawing. So let's say that so let's say that here we have, oh sorry, I have to put this inside. So sorry about that. So this means that if we have here the passing robot and here we have the ball, there are two distances, such that when the robot is here inside, it will make the calculation, and as soon as it comes here, it will stop the calculation, take the last value of the calculation, so the pass point that was found now, and use it for the pass. This is done for two reasons. So one is of course the computational power of the robot that we want to spare for all the stuff, but also because when the robot comes here, it will decide for an action. But if the module continue to work, it will continue to override the representation. So maybe as it was here, it say, okay, I'm going to do a pass to robot 1, but when the robot will come to the ball, the pass point for robot 1 could be changed. And this could represent a problem because maybe the robot then would throw the ball to the wrong place, or maybe he decide to make something, but at the end it will make something other. In order, so all this work that I'm present you that I did was tested just on the simulator. On real robot, I couldn't do that, also because at the moment there is not the possibility to measure, so to adapt the strength of the kick accordingly to the distance that we want to reach. In order, however, to debug the stuff on the real robot, I implement the following way. So every time this, I will probably also come back as soon as I will present you better the algorithm. But every time that the robot will perform an action, for example pass, for example shot, it will always tell you what it's going to do. I make an example. Let's say that here it will make the pass forward. It is going to play the sound where it say, I'm going to perform a forward kick to the player 1, for example. And this is very useful since we know what the robot is doing. I mean, if we wouldn't have this sound, maybe the robot could shot the ball to the door, but it could look like as a pass, even if it's not. But in this way, we can be sure that if something happen, if it's actually the intention of the robot to do that, or it's just something that happened randomly. So this is all for the main structure. I hope you get a general idea on what I talked about it. I'm not saying that this is the best way to solve the pass problem, but I thought that this could be a very nice way also to afford more complex tactics, because once that we have this field with all the point that could be reached or not, we are also able to make more complex tactics. For example, that one robot could start to work like that, and the same time, in the meantime, the other robot could try to throw already the ball here. But we can already know if the points here are available or not, because if it would be, for example, in this situation, none of this point can be used. So thank you for your attention, and yeah, please have a look to the other video.